I'll show you step by step how to download, upload, and push models to or from HuggingFace Hub. In particular, I'll address the thorny issue of pushing and merging adapters, including those that are in quantized form. And for our agenda, a few things we'll cover. First, I want to show you how to set up a Jupyter notebook that we'll use for downloading and uploading. I'll show you 3 ways using Collab and then hosted services like Runpod or VastAI. Then I'll show you downloading and pushing a 16-bit model. That's a full precision model. Next, I'll go through the same process, but this time using LoRA adapters, so assuming you've done some LoRA training. Then I'll go through that again and show you how it works with quantized LoRA adapters. Then I'll talk a little bit about the best model formats, so what level of precision, 16-bit or 4-bit for training, and also what the best model formats are, such as EETQ or AWQ if you want to get a fast and efficient inference. This tutorial has a notebook that you can get for free and follow along. So let's head over to the Trellis Research organization on GitHub and specifically to the install guides repository. Right there, you'll see a number of scripts, one of which we're going to use today, which is pushing to hub. Now you can just click on that script and it will give you a few options for launching it. I'll go through these options and then I'm going to go through the script in detail. So your first option is to open the notebook in Google Colab. This is the easiest option. It's also a free option. So I recommend this if you're probably doing things for the first time. The next option is you can run this notebook using Runpod or VastAI, which are hosted GPU services. This allows you to run much more powerful machines. So if you want to fine tune stronger, larger models, this is a good way to go. Also, you'll find as you get to an intermediate level using Google Colab, it's just slower. The GPUs are not as good as what's available using a paid service, and you end up saving quite a bit of time. So I pretty much always use hosted services because of the amount of fine-tuning tutorials I do. So just very briefly, I'll show you how to do that, Runpod or VastAI, or even your own GPU if you have one. Just click on this link here to follow the guide. And what you're going to do is download this notebook and you'll upload it to the hosted service or to your computer that has a GPU. Now, if you want to get started with Runpod or VastAI, it's important that you do run the correct Docker image. You basically need to have the right version of CUDA and PyTorch set up. That'll make your training using HuggingFace transformers easy. Fortunately, there's 2 templates that I've got set up here. One is for Runpod and the other is for VastAI. Let's just take a very quick look at those. So here on Runpod, if you click that one click and you've got an account created, it'll take you right to the template, which is exactly what you need. You can now select a machine. Most of these machines should work, but generally as you get to an intermediate level, you want to have something called flash attention, which allows for faster training enabled. And that means you want to use a more recent GPU. That's another problem with the free tier on Collab. By recent GPU, that means using an A100, a H100, or one of the best value ones is this A6000 here, which is 48 gigabytes of RAM. So I'm going to go ahead and deploy this. Just a note that when you click here on customize, it allows you to set the amount of space you need for your models. Typically, I recommend at least 3 times the size of the model on HuggingFace. So if you go over and find a model, let's say the Llama model, and it's got 13 gigabytes of weights on HuggingFace, I would allow at least 39 gigabytes because you're going to need to download the model and you'll probably want to save other versions after fine tuning. So here I'm going to start off with 50 gigabytes of space. The container, this is for the Docker image, needs to be maybe around 5. I usually make it 10 just to be safe. So let's set the overrides and make sure we can start the notebook and then we'll deploy. Okay, so I'm up and running with my Docker instance on Runpod. This is really quite quick. I just click on connect here, then connect to Jupyter Lab. And once I'm in Jupyter Lab, I'm going to take the script from the GitHub repo install guides and just upload it here just by clicking on the upload button. And now we're ready to go and run on Runpod. I'll now go through the VastAI setup. Again, I'm working here out of the guide. So I've clicked on the guide and opened up the LLM Notebook Setup. It explains how to set up Runpod, VastAI, Collab, and also setting up on your own laptop, which I won't go through here. VastAI is very much like Runpod. Just click on that one-click template. The one-click template should appear here on the left-hand side. It's the very same instance as used on Runpod. Now I'm going to select a GPU. So I'll get an RTX A6000 again, and I'll sort by increasing price. You can see that it's a bit cheaper. It's about 46 cents for the cheapest A6000 compared to, I think, around 70 cents or 75 on Runpod. So click on rent and then view the instances. And once this instance has booted up, which should be fairly fast, I'll be able to click here on this Jupyter button, and it'll open up a notebook in my browser, pretty much the same as in Runpod. And from that point on, it's going to be the same. So that's it for Vast AI. It's time now to go through the notebook and look at uploading, downloading models. I'm going to run it in Google Colab. So the first thing I'll do is check that I have the correct server, rather the correct GPU. I have a paid plan, 10 per month. So I have access to more GPUs, although they're not as good as the ones that are available on hosted services. If you have a free plan, there'll only be the option to go with T4 GPU. So you'll click on that and save. Now, once that's saved, you can click here on connect or reconnect. It'll say connect or reconnect on the top right-hand side. And that will set us up and ready to run the script here. Now, there are a few pre-installations that I'm going to do here, just upload or rather update my pip. Pip is used for installing packages in Python. So I want to make sure I update that. There's another package here, Skippy, that I think is pre-installed on Colab. So it's not necessarily, you don't have to install it again, but typically it's handy to have that as an install step if you're running in Runpod or Vast AI. The next step then is to log in with HuggingFace. This is needed if you want to access a gated repository. It's also needed when we're going to push models up to the hub. This should bring a pop-up where I'll have to enter in my settings, rather my token, my access token. So let me just get an access token here from the HuggingFace Hub Tokens page. I have one generated here. So I'll grab this Colab password and put this in here and log in. So I've logged in, and now what I'm going to do is set my cache directory. This is where the models will be downloaded. If I'm using Runpod, it will save them in the workspace directory. The same thing in Jupyter Lab on Vast AI. By the way, when you open Jupyter Lab on Vast AI, you'll actually be inside a folder structure. You need to enter the workspace folder structure and then upload your IPYNB notebook. So make sure your notebook is always in the workspace directory when you're using a hosted service. So again, just to recap, if you're using a hosted service, setting this cached here as just a dot means that you're going to save files into the workspace folder. The next step here is if I'm running in Google Colab, I might want to set the cache directory to be inside my Google Drive folders. So here's how I can do it. First, I will typically run this little piece of script. This is a technical matter. It makes sure that the UTF locale is set correctly. Sometimes you get errors when running scripts in Colab, and this addresses that issue by setting the preferred encoding. Now, these steps are optional. It basically will change your cache directory to be your Google Drive folder. Specifically within my drive, it'll be in the HuggingFace cache folder. This is useful if you want to save models and not download them again later. So I'll leave this as an optional step, but if you don't want to run it, you can just leave it and comment it out like I'm going to do here. Moving on to the installation, we're going to start by running, just downloading a full model in 16 bits and pushing it back up again to HuggingFace Hub. But later then I'm going to come back and I'll show you how to push adapters after fine tuning, and I'll also show you how to push quantized adapters. We're not going to do these installs just yet because they're only required for using adapters or quantization, but we will need to install transformers and we will need to install accelerate, which is needed for deciding that the model is going to go onto the GPU. Now, there are two ways to install transformers. There's the basic way here, which is pip install transformers. That's the most stable way to install it. However, there's a package that is currently under development and you can install it directly from GitHub. The benefit here is that it supports pushing 4-bit models up to the hub. That's something I want to show you later. So I am going to install this latest development version rather than installing the stable release here. So let's run this cell here. We'll install Accelerate as well, which is needed for setting the data type and also setting where the model will go, whether GPU or CPU. Okay, so we've done with the install, and now we're going to download a full precision model in 16 bits, and then I'm going to push it back up to the hub. So a very simple example, then I'll move on to pushing LoRA adapters, and lastly to quantized LoRA adapters, or rather a quantized model with LoRA adapters applied. The model I'm going to use is the Tiny Llama model. It's a small model, so it'll allow me to do the tutorial quickly. So here I'm setting my model path. I'm importing snapshot download, which allows me to download a full folder. Now there are two ways to download models. One is you could just copy the whole repository from HuggingFace Hub. That's what I'm going to do here. The benefit is it downloads the shards in parallel, which you'll see. That helps speed things up. You can also just load the model, and when you load the model in a notebook, it will automatically first download the model one shard at a time. So I'll show you that script below, but instead of downloading the model when we load it, we're going to pre-download the full folder, and then we're going to load the model from our machine. So here what I'm doing is I'm setting up the model we're going to download from the hub called hub model path, and I'm saying that I'm going to set a local model path to put the files, which will be in the cache directory, and I'm going to name it the same as the naming that's used on the HuggingFace Hub. Okay, so I've just run that, and next up I'm going to run the download itself. So to achieve this, you need to run a snapshot download, and here I've got to specify the repository that I want to download, and also specify where locally I want to put the cache directory and the local files. So here I'll just run this script, and it should start to download into my local. So you can see that it's fetching the 10 files in the repository, and it's downloading the safe tensors. This model in total is 2.2 gigabytes. So now if I look at my directory, you can see that Tiny Llama has been downloaded, and we've downloaded this model, and we've downloaded all of the files within the repository. So everything is ready here. Now that the download is done, we're going to load the model. Later on, I'm going to load it in 4 bits, but right now I'm going to load in full precision. So I'm going to comment out the quantization configuration. So when I load the model, I'll load it from the local model path, which is loading the model right here. And I'm going to set device map to auto. This is why we installed Accelerate. It means that Accelerate will automatically put the model onto the GPU if there is a GPU. I'm going to trust remote code, and this allows us to download models of a certain format requiring approval. And I'm setting my caching directory also to be equal to the local folder. So if there was any downloading, it would download them there. And because I've already specified a path on my local, I probably don't need to set the cache directory here, but it's good practice to have it set in case I hadn't previously downloaded the full folder. The last thing then is I'm going to download the tokenizer, and I'm going to download that as well directly actually from the hub. I could alternatively put the local model path there either, since I've already downloaded. So optionally, let's just put that in here because my tokenizer is, as you can see, it's already downloaded. So I've just run this cell, and that has loaded the model shards and also loaded the tokenizer. Now for this first run through the script, we're literally going to load the model and then we're going to push it up to the hub. So there's no preparing for fine tuning, there's no training or anything. And when it comes to pushing adapters and model to the hub, we're just going to push the model right up to hub. To push a model to hub, we'll set the org, which is the username. It's the first part of the repository slug. And we'll set the new hub model path. I'm going to set it as org/ and then the hub model path. Actually just grab the last part. That's what this split does here. So it will grab the name part of the model slug, and then I'm going to append on push demo here. So when I run this cell, it's just going to tell me that I'm going to push to Trellis, Tiny Llama 1.1b chat, and with this push demo on the end. So we can head all the way down to the push model to hub section. The model we're going to push is the model we loaded, so we'll run that cell. Then we're going to save the model locally using save pre-trained. We're going to save it to a folder that has got the same the same name as the repo that we're going to use on Hugging Face, which is new hub model path. So I'll just run that cell there. And then we'll actually push it to hub. Now, a few things I'll highlight here in the arguments. I'm passing the token as true, which means I'm passing authorization to push to my Hugging Face profile. Note that I do have to have logged in for this to work, which I did right at the top of the script. I'm limiting the shard sizes, the shard size of the model to 5 gigabytes. This is good if you want your model to be easy to load in a free collab notebook, so it won't overrun the memory. Typically, I set this larger though when I train larger models, because I don't want to have a ton of small shards. And lastly, safe serialization. This means it's going to be pushing the model weights as safe tensors instead of pytorch.bin or pickle files. The safe tensors have got added structure that makes them more efficient to upload and download. It's actually a bit of a security feature as well, so I always push safe tensors when possible. I've run that cell. Now let me just show you where that's all being saved. I've told it to save within new hub model path, so it should be saving within what we can see printed here, Trellis Tiny Llama 1.1b. So inside Trellis, then Tiny Llama, and we should see it within the push demo right here. And indeed, you can see that the model files have been saved right there. Now, they've also been pushed up to the hub. I can just click on the commit message here. And if I check the files, you can see that the hub files have been pushed. So let's just, in fact, I don't think I've run that push to hub yet. So I was seeing an old commit message from when I ran earlier. So we'll just give that a second to run. And then we're going to push the tokenizer. Again, we'll save the tokenizer and then push the tokenizer to hub. It's pretty much the same or similar parameters being passed. On rare occasion, you might want to load some other tokenizer from another repo and push that one. But we're just going to push the tokenizer that we had loaded previously. Now we can go back up here and yeah, indeed, this is my commit less than a minute ago. And let's check the files. And indeed, the BF15, so the 16-bit model has been pushed up. It's 2.2 gigabytes in size. And in fact, you can also see the tokenizer files have been pushed as well, which you can see from the script right down here. So what I did there is I saved both the model and the tokenizer. You can see now the tokenizer appearing. I saved it to my local. That's optional. You could just directly push, but I saved these files to my local and then I pushed the model to hub and then I pushed the tokenizer to hub. Now there is an alternative, which is that because I saved them locally, I could just directly upload the folder. And that's what this alternative here is. Basically, it takes a folder that's in my local path and it pushes it to a model on the hub. And optionally, you can set a branch to push it to. Branches are also called revisions in the Hugging Face hub docs. So you would uncomment this. Optionally, you can also create a new branch if you like this. And we might make use of that later when we push the 4-bit model. So that's the second way you can upload the folder. You can also use a similar structure to upload single files. And then the first approach we took was using the push to hub, where you specifically push the model and the files and specifically push the tokenizer and the files. Okay, so that's our first run through loading a full precision model and then pushing it up to hub. We'll next move on to loading a full precision model and considering the case where we have a LoRA adapter for training. And then we will push that adapter to hub and also merge the adapter and push the merged model up to the hub. This is our second run through. We're going to run in 16-bit, but this time we're going to push LoRA adapters. So everything at the top here, including logging into Hugging Face, is the same until we get to the installation. Here we're going to install PEFT, which is parameter efficient fine-tuning. Parameter efficient fine-tuning supports LoRA, which is a technique that's used for fine-tuning. Now, let me briefly recap how LoRA works with the help of some slides here. So if you have a language model with large matrices, say 1,000 by 1,000, might be the size of one of the matrices, it's common not to train that matrix. Rather than updating that matrix during fine-tuning, what we do is we build this kind of a sidekick set of matrix. So these are called adapters, and they're smaller matrices. And rather than training this large matrix, we instead train these smaller matrices. So we have the main model, which we actually keep frozen during the fine-tuning, and instead we train a smaller set of parameters called the adapter. And at the end of the training, what you can do is either save these adapters or you can merge them into the main model. And once you merge them into the main model, that gives you the merged model that you can push to hub and you can inference like a normal model. Now, it turns out that this type of approach is both quicker because you need to update fewer parameters, and it's also, it performs quite well and can converge faster than training all of the parameters. So this here is the LoRA, which is a low rank adapter. It's called low rank because it means that it has a small number of rows here. So you have two kind of smaller matrices instead of one large square matrix. So we've installed the library to support LoRA fine-tuning, and we're going to load the base model. I'm loading here a 16-bit version of TinyLlama. The original TinyLlama is a 32-bit model. You could load with that, but I like to load a clean 16-bit model. Most models on HuggingFace are 16-bit. So I've downloaded this repository here, and this repo contains the model weights of the base model. And once that's done, I'm going to load the model. And the loading is going to be done in 16-bit. We're not doing any quantization yet. That's both of the model and also of the tokenizer. And once the model is loaded, we're going to load this sidekick or adapter. So the sidekick that we're going to load, let's just take a look at it. We're going to run this here to calculate the trainable parameters. Once we've loaded the model, we're now going to apply these adapters to many of the matrices. Now, we're not going to use the adapters for every single matrix in our model. We're only going to apply it to a selection of modules. And the way you decide what modules to apply it to is handled here in the target modules. Now, I'm applying these adapters to these specific modules, the Q projection, KVO, gate up and down. So these are specific modules in the attention and the linear layers of the model. And this is a typical specification. After that, I'm going to run gradient checkpointing. This is an extra step that allows you to reduce the VRAM required for training. So it's something that's commonly done. And here you can see a snippet of code that's going to take the model we loaded, and it's going to generate a LoRA adapter or set of LoRA adapters for all of the matrices within the model. So we'll go ahead and run that. And once we have applied the adapter or generated the adapters, we can see the number of trainable parameters. There are indeed 1.1 billion parameters because it's TinyLlama is a 1.1 billion parameter model. And of those, 0.57% are trainable. So you can see that we're only training a very small number of parameters relative to the total in the original. And that's because we're using these very small matrices, the adapters, instead of training the full original model. Of course, in this tutorial, we're not going to go through the training, but I did need to set this up so that we have a model that has a set of adapters beside it. So I can show you how to push these adapters to hub and also show you how to merge the adapters on top of the original model. So typically here, you would take all the steps around updating your tokenizer, padding, putting your data set in place, running evaluation before training, running evaluation afterwards. And you can check out the Trellis Research YouTube channel for plenty of videos there covering chat fine-tuning, unsupervised, supervised fine-tuning, and much more. But in this video, we're focused on pushing adapters in the model. So let's set up the name of the model and repo we want to push through. So I'll run this cell here. This means that we want to push our eventual merged model to this repo right here. Before we push the merged model though, you may want to save the adapters, which are quite small. So if you want to save those adapters, you can set up another repo, maybe a repo with the same name, but ending with -adapters. So let's run this cell, and we're now setting up to push to this specific repo here, only the adapters. Now, there are three different ways you could grab an adapter. First off, if you've run a training process, you could grab an adapter from a set of saved checkpoints. So you might have multiple adapters saved from the training process, and you might decide you want to pick one from in the middle because it's good performance at that point, and that's where it had the minimum loss, for example. Another way you can pick an adapter is you could just grab one from HuggingFace Hub. You may have trained one before, somebody else may have trained one, and you might want to merge that onto a base model. So this is another approach. Now, if you grab a checkpoint, or if you grab an adapter from the hub, you do have to apply that adapter to the base model. So we have the model variable, that's the very first model that we loaded earlier, and you would want to apply this adapter you've just grabbed. You want to apply that to the model to create a model with a LoRA. So if you want to take option A or B, don't forget that you have to apply the adapter before you'll be able to merge it. What we're going to do though is a third option, which is simply setting. We're going to take the model that we previously loaded with the LoRA. So before the training, we created a model with LoRA. And assuming we put that through a full set of training and we were happy with the final result. So we didn't want to take an intermediate result. We wanted the adapter and model in the final state. So in that case, we'll set the adapter we want to push equal to the model with LoRA. And we'll also set the model we want to push equal to the model with LoRA. Now we're going to use this here to directly push the adapter. And this here, the model to push, we're going to do a merging step on that, and then we'll push it up to hub. So let's start by simply pushing the adapter to hub. So we'll take this adapter to push, and we'll use the save pre-trained method. That's going to allow us to save it locally. So let's make sure that I run this piece of script here to set the adapter and model to push. Now we'll save the adapter locally. And now we're going to push that adapter to hub. So I'll just show you here. We should have saved the adapter within Trellis, and it should be saved somewhere here within the adapters folder. And you can see indeed the adapters with the adapter config are here on our local. Now I've just pushed the adapters to the hub, and you can see right here, they've been pushed less than a minute ago. And these are small files. The adapters are much smaller in matrix size than the original model, so it's only 12 megabytes. Okay, so now we have a copy of the adapter on the hub, and you might want to do this because it's just an easy small file that you want to save, but more often you'll want to actually merge the adapters onto the base model and then push that model to hub. You don't really want to leave them separate, because if you inference a model with a separate adapter, it's requiring an extra addition step every time you forward pass through the matrices to generate new tokens. So it's inefficient. And also a lot of libraries won't even support adding adapters on the fly. So let's look at how we merge an adapter onto a base model. It's actually just a one-line piece of code. You take the model to push and you run merge and unload on that. So we'll run merge and unload. And now that we have this model to push, remember this is the merged model we want to push. We don't want to push the original model, so we'll comment that out. So we're going to take the model to push and we're going to save it. And we're going to take the model to push and we're going to then push it to hub. So what we expect now is that this merged model is going to be saved locally. It'll overwrite the model in the first pass through this script. And second of all, that model will be, it'll be pushed up onto the hub. So we should have a copy of a merged model that's going to be up on HuggingFace at the address or the repo that we've specified. And there it is. We have the adapter merged onto the base model. And that brings us to the end of the second demo, which is taking a 16-bit model, creating a LoRA adapter, showing you how to push the adapter, showing you how to apply the adapter onto the base model, and then showing you how to merge that adapter and push it up to the hub. Just like I showed on the first pass through, you can also push the tokenizer, or you can just upload the full folder structure. So with that, we'll move on to the third pass through of this script where I'll show you quantization. We're going to run for the third time with quantization. So I'm starting at the top of the script. I have logged in with HuggingFace, and now I'm at the installation phase where I'm going to install bits and bytes, which will allow us to do a fine-tuning in quantized form. So let's run those scripts and we will download the repo. I've reset my notebook just so there aren't any variables that I'm accidentally reusing. And I'm going to load the model this time with the bits and bytes configuration. So this is a 4-bit format. It's technically double quantized, so it will apply quantization scale to the 16-bit weights to bring them to 4 bits. And then it will quantize the scale that's used for that quantization. It's called NF4, which is normal float 4. It's actually a normally distributed pattern for the quantization that improves the quality significantly over a naive 4-bit quantization. Now, when we load the model, we need to pass the quantization config, which is what we defined up there above. And we're going to run with all the same parameters. And also, we're going to load the tokenizer as per usual. So I'll just scroll up here and see how things are progressing. Looks like we're just installing bits and bytes, and then the repo download will start. Now, in the meantime, I'll keep moving on. We're going to use LoRA fine-tuning, or at least proceed as though we're using LoRA fine-tuning. So we will again have a function to count the number of parameters that we're making trainable. And we're again going to apply adapters to the model. So we have the base model and we have the adapters that we're going to create. Here are the modules that we're going to target with these adapters. And here is going to apply the modules. Now, additionally, we can run this little line of code here to prepare the model for k-bit training. This is useful for quantization. I think it again reduces memory usage. So here we're going to create a model with LoRA, which is again the base model with the adapters beside it. So I'll run this script here. But this time, the base model is quantized in 4-bit. At least certain modules that we've chosen this time the model is quantized in 4-bit. And we've got the adapters. Now, the adapters are always in 16-bit, which is a bit confusing, but the LoRA adapters are always in 16-bit. But the base model, which is frozen during the training, that's going to be in 4-bit. And you can see here that the trainable parameters are going to account for 1% of the total parameters. And you can see in total, we have 600 million parameters. Okay, so next up, we're going to look at pushing the adapters in the model. So you have to imagine that we've loaded a model, we've loaded it in quantized form, we've created the adapters, so we've now got a model with adapters. And what I'm going to show you now is, assuming that has gone through training, we're going to push the adapters, then we're going to apply the adapters onto the base model, and we're going to push that, and that will be a 4-bit model. So let's start off. We'll again define the organization and the path on the HuggingFace repo where we're going to push this model. Likewise, we'll define a path where we're going to push the adapters. Nothing is different here so far. For choosing an adapter, we're again going to assume that we want to push the model and adapters in the final state at the end of training. So we'll just set the adapter to push equal to the model with LoRA, and we'll set the model to push equal to the model with LoRA as well. Now we're going to push that adapter to HuggingFace Hub. First, we will save it. So I'll just save that, and then we will push to HuggingFace Hub. So that adapter is now being pushed. Remember, again, adapters are always 16-bit, so there's nothing too much different so far. Next, we're going to merge the adapter. So there are 2 ways to do this. I'll start with the simplest way. The simplest is there is now the possibility of taking the 16-bit adapter and merging it with the 4-bit model. So it's actually still quite easy. It's just model to push, and then model to push, merge, and unload. So you use the same line. And thanks to some recent updates, I've given some credit at the top of the script. You're able to just merge those 16-bit adapters onto the 4-bit to generate a merged 4-bit model. And not only can you merge to a 4-bit model, you can just continue with the same approach and save that 4-bit model. And further, you can even push the 4-bit model to the hub. So let's take a look as that model gets saved. Looks like it's already saved. Should be saved in the Trellis folder, and should be saved here under push demo. And indeed, we can see there is a file saved. If I hover there, you can't see it very clearly, but we have a safe tensors file that's just under gigabyte in form. Let's take a look at what we've pushed. So here we have pushed, and you can see that we're now pushing with a quantized configuration. And you can also see that in the model card, rather in the files here, we have pushed a quantized version of this model. And next, we can just push the tokenizer, which is very much the same. Or alternatively, as I showed you before, instead of pushing the model and the tokenizer each, you can just upload the folder. That's providing that you have saved the tokenizer there in advance. If you just want to save the tokenizer, let's see if the tokenizer is there already. It looks like it isn't, which makes sense because we haven't run that yet. So just comment out pushing to hub and allow that to be saved. And here now, if I just open and refresh this push demo, you can see now the tokenizer has appeared, which is what we expect because we have saved that. Now there's one other way that you can push the adapter. This is pushing in 4-bit, just as I showed you there. If we look at the config.json, this has been pushed as a 4-bit model. This means it's smaller on the hub, so it's going to be a smaller model. It'll be quicker to upload and download. However, it's not quite as compatible with libraries for doing inference like text generation inference or VLLM. So if you want to do something for inference, you actually want to push a 16-bit model and either inference that 16-bit model or quantize it to a format like AWQ. Now, I'll talk specifically about that a little later in the video, but first, let me just show you an alternate way that you can push a model to hub. So if we go back up to where we merged, you'll see that we just merged the model, which was merging the 16-bit onto the 4-bit. Now, the other thing that we could have done is we could instead have reloaded a base model, which I'm calling option X here. So here in option X, what I do is reload a model and reload it in 16-bit. And then I apply the adapter that presumably has been trained onto that 16-bit model. So just to recap, up above in the script, I'll have loaded a 4-bit model. I'll have trained a 16-bit adapter attached to it. Then I'm discarding that base model. I mean, I'm not actively discarding it, but I'm just forgetting about it. And I'm reloading a 16-bit model. And then I'm applying the 16-bit model, LoRA, onto the base model. That's what I'm doing here. Now, why would you do that? Why would you not just train the 16-bit in the first place? Why bother quantize? Well, if you want best precision, that's correct. You shouldn't quantize in the first place. You should just start with the base model in 16-bit and train a 16-bit LoRA adapter. However, if you're using a free collab notebook or you've limited VRAM, you may not be able to train the full 16-bit of precision because you don't have the VRAM required. So in that case, this allows you to train using a quantized base model. You get the 16-bit adapter and then you merge it. So let's just try that out. So I'm now loading a model in 16 bits, applying the new hub model adapters. And now I'm going to merge that model. So I'm now merging this, which means applying the adapter onto that base model. And now I can push this merged model. So let's save it. Let's push it to hub. And what we should see now when it's being pushed to hub is that it should not be a quantized model because even though I used quantization for the training portion to get the adapter, I applied that adapter onto the base model. We'll see what happens here. And now we have that commit that's complete. So let's take a look. And let's in particular take a look at the quantization. So you can see that the quantization configuration has been removed. And that's because we have now pushed a model that is 16-bit. And it's also going to be a larger model, so it'll be slower to download or upload. It's 2 gigabytes in size. But it has the benefit that with a 16-bit model, it's going to be compatible with inference, which is one of the next things we'll talk about. Before I let you go, I want to talk about the best model formats for training, how to decide whether to use quantization or LoRA, and I'll also talk about the best formats if you want to do inference on a more production scale. First, let's talk about training. So there are two ways to think about it. There's the cheap way, and then there's speed and quality. If you're just getting started, cheap can be good. So using a free Collab notebook can be a good way to go. If you're going to use Collab, using quantization will help you to fit larger models. So it'll allow you to fine-tune models probably even up as big as 13 gigabytes or maybe a little bit bigger if you're using quantized LoRA. Now, I always recommend using LoRA, even if you're fine-tuning for production quality. LoRA tends to perform better, it converges faster than doing a full fine-tune, and it also uses less memory. So I would still use LoRA if I'm optimizing for speed and quality, but I wouldn't use the quantization because that does degrade the quality a little bit. Now, if you're looking for speed of training and just more convenience, I do find it handier to use services like Runpod or VastAI. The larger GPUs are just a lot faster and they allow for using more advanced features that you'll see in a lot of my other videos. Moving on now to look at inference. So the format in which you save a model has a big influence over how you can run that model in production as an API. There are a few ways that you can run models I've covered in other videos around server setup and inference. Notably, there's text generation inference and also VLLM. Now, they don't natively support loading a model from NF4 4 bits. So unfortunately, if you push a 4-bit model to hub, it's handy just for testing and you can pull it back into a Collab notebook or inference it with Python, but it's not easy to inference it. In fact, I don't think it's possible to inference right now with any of the main libraries for setting up APIs. Therefore, if you're going to run in a more production type environment and you want to run something that's in the best quality, let's say in 16 or 8-bit, then I recommend training in 16-bit using LoRA. And once you have it in 16-bit, push that model in 16-bit to the hub, and you can use inference with TGI, with EETQ. This is an 8-bit form of quantization, but it's done on the fly. So if you have your model in 16-bit on the hub, you can inference it using TGI and EETQ, which is very fast and also is good quality because it just quantizes on the fly to 8 bits. The other option you can look at is if you really want a 4-bit model for production use, then you should train the model in 16 bits using LoRA. So don't use QLora. But then afterwards quantize with AWQ, which is one of the best quality quantizations. Now, this does mean running a script. I have a video on AWQ quantization that you can check out, but allows you to get reasonable quality, a little bit of degradation while getting fast inference. Once you have your model in AWQ, you can then inference it, set up an API with TGI or with VLLM, and you can check up my inference video for more details on that. So all of what I showed today around quantizing to 4 bits and then pushing it to the hub, really that's mostly useful for learning or for doing small tests by yourself. You can train in 4-bit using QLora, and you can then do inference using Collab or Python just by reloading the model and doing some quick inference that way. But it won't be easy for you to run a production grade API using that 4-bit quantized model. Now, there's one little side case, which is if you really want to use a free Collab notebook but generate a production type model in 16 bits, the way to do that is to fine tune using QLora and then merge your LoRA back onto a reloaded 16-bit model. That's the last thing I covered when I went through the Collab script. And that's kind of a workaround that allows you to fine tune with low memory with a free Collab notebook and still end up with a 16-bit model that you could then do inference on using either the techniques here, which would be running in TGI with EETQ, or quantizing that 16-bit model to AWQ and running with TGI or VLLM. Note that you will get some more quality degradation if you do that approach, but still, it might be interesting for some of you to do it. That's it for this video on uploading and downloading models. If you want to move to more advanced fine-tunings, for example, chat fine-tuning or long context or supervised or unsupervised, then take a look at some of those videos on this channel. You can find all of the scripts from today on Trellis Research GitHub repository. I'll put a link below, and there you can find the installs guide repo, which contains this script, and also the guide for how to get set up on Collab or Runpod or VastAI. And just one last thing before you go. A lot of these videos, they have updates that are needed over time. That's because a lot of the libraries are advancing and there are little tweaks or upgrades. So I've started a simple newsletter It's available at trellis, trelis.substack.com. That's trellis.substack.com, trellis with one S, rather with one L, trelis. But anyway, I'm just using that to share every time I have a new video that comes out, and also give little ad hoc updates if there are some upgrades you need to make to packages and you think that would be useful for you. All right, folks, as usual, let me know your comments down below in the comments.